Good morning, guys. Mr. Milton here. Today we're going to talk about bisectors and triangles. At the end of this video, you should be able to find the missing side lengths and draw conclusions using perpendicular bisectors and angle bisector theorems. And you should be able to explain how to find missing side lengths. Start with some vocabulary. If we know what we're saying, then we can know what we're talking about. So straighten up my page. Hopefully it's the last time on this first side. Alright. So first, perpendicular bisector. Okay, it means what it says. Perpendicular, two lines that intersect at a 90-degree angle. Perpendicular means. Bisector, a segment or line or ray that cuts a segment in half. Two congruent pieces. We'll just say half. Okay, so a perpendicular bisector does both of those things. It cuts a line in half and intersects it at a 90-degree angle. An angle bisector is a segment, line, or ray that cuts an angle in half. Okay, so perpendicular bisector happens to a line, angle bisector happens to an angle. Okay, so there's the difference. Okay, so now let's jump into the perpendicular bisector theorem. The perpendicular bisector theorem says if a point is on the perpendicular bisector of a segment, then that point is equidistant. Equidistant. It's kind of an easy word. Equal distance from the endpoints of a segment. Okay, and that makes sense since perpendicular bisector means that it's bisector means it's in the half. We'll look at some examples here to show why it makes sense. Okay, so first example, it says given CD is the perpendicular bisector of AB. Prove that CA is congruent to CB. So we're going to kind of prove this theorem here. So what's given is that CD is the perpendicular bisector of AB. This line, or segment, CD, cuts AB in half because it's the bisector. So what we know is that AD is congruent to DB. And it's perpendicular to AB because it says it's the perpendicular bisector. That's given. We don't have to think about it. So it's a 90-degree angle. Now we want to prove that CA is congruent to CB. This is a triangle proof. Okay, so we'll talk through it. We don't have to do the two-column proof thing, but we'll talk through it and you'll see that we have reasons and statements. So our first statements, AD is congruent to DB. That's given. Definition of perpendicular bisector. And then angle CDA and angle CDB are 90-degree angles. Again, definition of perpendicular bisector. Those two things work out. Okay, back to our triangle proof days, just a couple chapters ago. We should be able to say that CD is equal to CD, right? Because of the reflexive property. It has to be equal to each other because it's itself. And now what we should see is that for these two triangles, CAD and CBD, they are congruent to each other. They're congruent because of side angle side. Side angle side. So I'll just write this down. Triangle CAD is congruent to triangle CBD by side angle side. Okay, now because we know that these two triangles are congruent, then what we can say is, well, if these two triangles are congruent, that means their corresponding parts are congruent. And so we should see that CB and CA, CB, CA, are congruent to each other as well because of CP, CTC. Corresponding parts of congruent triangles are congruent. And so there we have it. We've proved that CA is congruent to CB. Get that little tilde. And that is the perpendicular bisector theorem. And notice that no matter where I move C, so if I move C here, it's still the same. CD would still be congruent to CD. If I moved it here, CD would still be congruent to CD. If I moved it on the line, then that's even easier to know that they're going to be equidistant. If it's down here, it's still going to be equidistant because it's on the perpendicular bisector. So that proves the perpendicular bisector theorem. Okay, let's look at the next example, kind of using this a little bit more than proving it. It says which segment is the one getting cut in half? Okay, so what we want to see is where's the perpendicular bisector? Well, the perpendicular bisector, well, the segment that's getting cut in half, let's go and answer that question. We see that this, and I should maybe name this so I can refer to it while I'm talking. Let's just say CE and ED are congruent, right? So which segment's getting cut in half? CD is. So which segment is the perpendicular bisector? So since CD is getting cut in half, that means AB must be the bisector. Okay. All right, next question says AD equals. All right, let's try to find that out. Well, what we'll know is that this is 4. Okay, since this is on the perpendicular bisector, since D is on the perpendicular bisector, then we know that this has to be equidistant from the endpoints of the segment. So since DB is 5, then we know that AD has to be 5 as well. We kind of did the same thing with BC. Since AC was 4, then we know that BC had to be 4 as well. Okay, and that's the perpendicular bisector theorem. All right, so pretty straightforward. Flipping to the back. The converse of the perpendicular bisector theorem says if a point is equidistant from the endpoints of a segment, then the point is on the perpendicular bisector of a segment. Perpendicular bisector. Basically the same thing. Going converse just means we're starting with the conclusion of our original statement and going to the hypothesis of our original statement from chapter 2. So, it says find the value of x and explain how you got to it for this example that goes with this. Well, here we see that HF and FG are the same distance. So F is the same distance from G, F is the same distance from H. So since it's the same distance from the endpoints of HG, what we know about this is, hey, F must be on the perpendicular bisector. So EF is the perpendicular bisector. So with our markings, we can say, oh, well, 5x minus 3 equals x plus 5. Solve. I'll add 3 to both sides. Subtract x from both sides. So 4x equals 8. X will equal 2. Okay. EF is the perpendicular bisector. So HE is congruent to EG. Okay. Okay. All right, so distance from a point to a line. When we talk about distance from a point to a line, so like point F to a line, we always talk about the length of the perpendicular. So when we talk about distance, we talk about the length of a perpendicular segment. Okay, and that, for us, it just means the straight line. If I say, hey, how far away is F from E, I want to talk about the straight line. I'm not going to say, well, F is this far away from E. Well, why are we not going straight to E? Or if I say, hey, run to E, you'd go to the straightest line you can to E. So what all that means is that we're looking at a straight line. Okay, and that'll make us a perpendicular. Okay, so when we talk about the distance from a point to a line, that's what we're talking about, the perpendicular distance. All right, now going on to the angle bisector theorem. Okay, angle bisector theorem says if a point is on the bisector of an angle, then the point is equidistant to the sides of the angle. Equidistant to the sides of the angle. Okay, and that's just what we were talking about. Okay, so when we're talking about equidistant, if I say how far away is F from D, I'm asking about the perpendicular distance, the straight line distance. All right, so let's answer these questions. Name the angle bisector. So name the line that cuts the angle in half. Well, the angle, we have ACE. The line that cuts it in half or divides it in half is CF. CF is the angle bisector. or I guess I should say ray CF. Okay. How do we know it's an angle bisector? Well, we can tell because angle, we'll say ACF is congruent to angle ECF. And yeah, you could have said BCF or DCF instead. Okay, since F is on the bisector of angle ACE, we'll say that, or BCD, then F is equidistant to side AC and side EC. Okay, it says which symbols are necessary in order to say that FB is congruent to FD. Symbols that are necessary, we need to make sure that we're talking about the perpendicular distance. Okay, 90-degree angles. We need to make sure that we're talking about the perpendicular distance. And so since we have that, we can say, okay, we have that, so and I can solve for x and say these two have to be the same. 5x has to equal 2x plus 24. 3x will equal 24. That means x equals 8. And so if they ask me what FD is, well, that's 8 times 2, 16, plus 24, 40. And that should be the same as 8 times 5, which it is, 40. All right. The converse of an angle bisector, if a point on the bisector of the angle is equidistant from the sides of an angle, then the point is, oh sorry, I said the bisector. I said that too early. On the interior of the angle is equidistant from the sides of an angle, then the point is on the angle bisector. Okay, so essentially saying not a point here, we're saying, oh, it's equidistant from these angles. So we're saying inside the angle, then it's on the angle bisector. So similar to our perpendicular bisector there. Okay, so now answering this question, it says how far from K is ED? So here's ED. And so we see that K is 10 units from EH. And so K has to be 10 units from ED. Since K is equidistant from ED and EH, okay, and I'm not just assuming that. They give us this markings that say that these two are equidistant, right? Since ED and EH are K is equidistant, then K is on the angle bisector of angle DEH. I could say angle E, I guess, in this case. All right, and so what that helps is we can see that, okay, this is the angle bisector. And so I can set up this equation as 2x equals x plus 20, or x equals 20. And angle DEH then, DEH, that's this whole thing, will be 2x, so 2 times 20, and 20 plus 20. And so that'll give us 80. 80 degrees. All right, so pretty straightforward looking at the angle bisector theorem and the perpendicular bisector theorem. A couple examples. Hopefully now you're able to do this, and I'll see you tomorrow.